Okay, hopefully you can all see that.
Yep, looks good, Helen.
Brilliant. Right, so thank you for allowing me to talk to you about our topic, ocean acidification. So I'm Helen Findlay from Plymouth Marine Laboratory, and I led this chapter or this topic in collaboration with Yuri Artioli from PML, Silvana Birkenoff from CFAS, Sue Hartman and Martina Steisner from the NOC, and Pablo Leon from Marine Scotland. So I'm going to go straight in what is already happening. Well, we have high confidence, as most of you hopefully are all aware, that atmospheric carbon dioxide is increasing in the atmosphere. Last year it surpassed 414 parts per million, and that's increased by approximately 2.4 parts per million per year over the last decade. And these are figures not just from around the UK and Ireland, but actually from the global carbon budget from Fidlingston, which was published this year, of the global carbon budget last year. So you can see that atmospheric CO2 is going up. The ocean naturally takes up some of that carbon. It actually has been taking up about 26% of the atmospheric carbon dioxide over the past few decades. And that's really important because it actually mitigates against additional atmospheric warming. And so the oceans are playing a key role in helping to regulate our climate. But that comes at a cost, and that's where we get into ocean acidification. So as the carbon dioxide goes into the water, it reacts to form a weak acid, carbonic acid. And that's resulting in the oceans becoming more acidic. Now, we have good high confidence that we know that the North Atlantic Ocean in particular has very high levels of anthropogenic carbon dioxide, and that's because of the way the ocean circulation patterns happen. So in the North Atlantic and the Arctic regions, we get a lot of CO2 going into the water because they're colder, but also because the deep water is formed in those regions, and that goes down into the deep waters and forms part of the global ocean circulation patterns. So we know that carbon dioxide is going into the water, is reacting, and then it's producing this acidity, this increased acidity, and that's resulting in the surface waters becoming more acidic, and also the bottom waters. And we have high confidence both from observations and models. So here, this is taken from the reports. These two figures show the trends in pH just for around the UK and Ireland between 1990 and 2015. These are model maps. And I've just, in black here, I've highlighted the regional averages. So for the Greater North Sea, the Celtic Sea and the Bay of Biscay. And you can see that in the surface waters, we're sort of talking about an acidification rate of about 0.002 per year. It doesn't sound a lot, but that's a logarithmic scale for hydrogen ions, so it's a significant contribution. What's interesting is if we map the two observation stations that we have, and we do just have two in the UK at the moment, we can see actually that because of the subdecadal variability that we get in these regions, these nearshore regions, we actually get much faster rates in these nearshore locations. And that's really resulting because of these high fluctuations. As you heard from Jonathan, we've got a lot more salinity, fresh water input that will affect the pH in these areas as well. At WCO L4 down in the south, we have slightly slower rates because we have a slightly longer record, but again, they're still faster than what we're seeing in these average offshore locations. In the bottom waters, we actually see greater acidification rates in those regions as well. When it comes to the biology, we have medium confidence that some species are already experiencing ocean acidification impacts when they're exposed to short-term fluctuations. And we can also expect that some of these species are going to be quite useful for indicators. So this really comes from data from pteropods and gastropods that float around in the mirror plankton. So these are free-swimming snails or the larvae of some of the benthic snails that have these shells that are actually predicted to dissolve when we put them in more acidic conditions. And so we can measure the amount of dissolution in those shells from no dissolution through to quite severe dissolution here at the bottom. And Pablo Leon and his team up in Marine Scotland have been monitoring both the chemistry but also how this shell dissolution has changed through time. And what they were able to show is that declining aragonite saturation states result in more severe amounts of dissolution, shown by these black bars here, where in periods of increase in aragonite, so that's when we're expecting the pH to be increasing a little bit, then we have less dissolution. So we have less confidence in this because we have much shorter time series data, we have much shorter observations, and that's really when it comes back to one of the challenges that I'll mention in a minute. So what could happen in the future? Well, we have lower confidence than the observations of what's happening today because we're relying again on models, and models not necessarily capturing all the dynamics, especially when we're thinking about the really nearshore coastal environment because of those high levels of variability. But we do know that the pH will change. We expect that chemistry to continue. We're expecting to see similar rates of change depending on what emission scenarios we use by the mid-century. So this is model plots again for the region for 2 emission scenarios. On the left here we've got mid-emission scenarios, and on the right is high emission scenarios for the period between 2000 and 2050. And again, I've just put in the average rates here for the Greater North Sea, Celtic Sea and Bay of Biscay, and you can see they're relatively similar to what we're experiencing today in the surface waters. If we go to higher emission rates, you can see that they are slightly faster acidification rates. So we also expect that the bottom water will be changing, and we can measure, we can project using models the area that we expect of around the UK and Ireland that will become essentially corrosive to these calcium carbonate forms of shells. So when we think of aragonite saturation state and it becomes undersaturated, that's when it's going to become corrosive. And what you can see is that we're expecting, even in the next 10 to 20 years, that on a monthly seasonal basis, we will be experiencing increasing frequency of these undersaturated events. So as we go through the next century, and to the mid-century and then towards the end of the century, again, it depends on emission scenarios, but we're projecting with the high emission scenarios that actually over 50% of the area of the North Sea, Celtic Sea and these regions will be constantly undersaturated, and over 90% will experience periodic undersaturation, and that's of significant concern and really highlights the need to keep emissions as low as possible going into the future. I've just added here the bullet point at the end that high levels of variability in the near shore actually have the potential to allow some coastal species to be able to adapt to acidification, potentially maybe more than offshore species. And I've put low confidence in this because most of this comes from laboratory work or kind of hypotheses studies where we know that species that experience more variability in their natural environment actually have more capacity to adapt to varying environments in the future. However, all species could also be at higher risk from these extreme events that we're seeing. So if we're getting increased frequency of these extreme events, then that actually could be detrimental as well. And quite often, especially historically, we know more about temperature. We know that extreme temperature events can wipe out populations just in a matter of days or weeks. Similar sort of thing could become apparent with acidification potentially as we go into the future, but it's still low confidence. We need a lot more data and a lot more analysis on that side of things in terms of the biology response to acidification. So that brings me to the key challenges that we identified. We've got 3 here that I've listed, and you can see the challenges and then these last bubbles, which I'm afraid are a little bit small, but it's all in the report. Represent what we can kind of do to address those challenges. So we highlighted the lack of observations, and this really prevents us from having a good understanding, particularly in the near shore. As you saw, we just have 2 UK stations that are monitoring on a high enough frequency that we can make good analysis of what's going on in those near shore locations. And we really need to get a better handle of what's going on around the rest of the UK and Ireland. And also the lack of observations prevents us from really being able to establish the links between the biology and the chemistry as it changes. So being able to attribute any change that we see in biology can only be done if we have those corresponding results and monitoring observations for the chemistry and the physics. So what can we do? We need to develop and sustain our monitoring networks. We need to better link those monitoring between physics and chemistry and biology. We also need to be aware of multiple stresses. So ocean acidification is not going to act in isolation. and future studies need to represent that. So we need to be conducting local ecosystem and societally relevant experiments. To date, most of the experiments have been done on a kind of global average level, what's going to happen at a kind of global average acidification level. But we know, again, that we've been able to show that nearshore variability really matters, and we need to start to be taking that into account so that we can actually provide that evidence to show what's going to happen locally. And finally, data accessibility. So it's very difficult to produce these types of reports, and we've recently was involved in the OSPAR quality status review as well. And data is not necessarily readily available or accessible to bring together in that holistic way. So we need to be working together to across the community to be able to bring together these time series, vocabularies, metadata, calibration exercises, etc. So that was a real whistle-stop tour, and I'd be really happy to take any questions later on, or feel free to email me or get in touch, and hopefully we can discuss more. Thank you.
Brilliant. Thanks, Helen. I could see a question already coming into the chat for later on, so that's good to see. So keep those